one convenient rewriting that we can do for this formula here. So this formula is completely correct and honest and very fulfilling for all the again, I'm just I wanted to do the our hats here, but I didn't, so that's a cubed. So this formula here is completely acceptable. There's nothing wrong with it. If I happen to know the polarization throughout my my object, then I just compute the potential this way. If I get the potential, I get the field. It's all sorted out. However, there's a kind of convenient reinterpretation of an equivalent situation giving us absolutely exactly the same potential. And here's just to introduce the idea of the bound volume and surface charges. So how does it go? So again, here we put our mathematical hats on for a few minutes, and we use essentially almost the same identities that we flashed last time. Once again, the derivation itself is a one-off thing. However, the end result will be the thing that you can really walk away with and remember. So what do? We will just massage this expression here into a more convenient form. Okay, so let's do it. First, I rewrite this this r over r cubed as, again, the gradient of a scalar. So this r over r cubed is just the gradient with respect to the prime coordinate of 1 over this distance, r minus r prime, exactly like we did last time. Okay, and I just plug that into my expression for the potential here. And now I do a partial integration using the result of applying the divergence on the product of a scalar and a vector function. Okay, so here what I'm doing is that I'm writing that p dot the gradient of that scalar function is really the divergence of the product of that p vector divided by that thing, which was the scalar function. But then here I need to correct for the derivative of p that I induce when I do this. So I just have to remove the divergence of p in here divided by this. Okay, so this is really just the absolute same identity that we used last time. Okay, but now in a sense it's even simpler because we're done. Okay, and why do I say that we're done? It's because these two terms that you get from this have a very convenient interpretation. So the two terms that you get from doing this partial integration here are, first, a surface term, and second, a bulk term. And the idea is that the surface term here is the potential that is associated to something that lives in the surface of your volume but has a certain surface charge density. The bulk part is just, again, the potential that comes from a charge distribution inside the bulk. Okay, so be careful here, because we were originally integrating a volume density of dipoles over the volume. Now we have rewritten that thing as a surface and a bulk density of charges. So the electrostatic potential created by a volume density of dipoles has an equivalent interpretation in terms of the electrical potential created by both a volume and a charge, a surface charge density. Okay, and we'll give a little bit of an intuitive explanation why this is the case. Okay, so but for now, just quoting the formulas, this expression for the potential has the form of the potential coming from a distribution of charges on the surface and the potential coming from a distribution of charges in the bulk, where these densities at the surface and in the bulk are called the bound densities. So bound surface and volume densities. And their mathematical expression in terms of the polarization is just given here. The surface charge density is just the in product of the polarization vector with the normal at the surface point where you're evaluating it. And the bound charge density is just minus the divergence of the polarization. Okay, and we'll do a few drawings for you to understand where that comes from. Okay. So rho B at R. So this is inside the volume where I've got non-zero polarization. The bound charge density is minus the divergence of P. Okay, let me maybe try to illustrate that with drawings to help you. Yes, question. Yeah, because here I'm integrating over the source charges inside the volume. So this is d tau prime. Maybe there's a, so here the integral is over the primed variables. Okay, but here so you have to interpret this equation here as being valid for positions are inside the volume. Because once again, this is a local equation. So the bound charge density at a certain point in space is the polarization at that space whose divergence you've taken. So outside the volume that you had, this polarization is just zero because there's no density of dipoles. Then the bound charge density is only non-zero in the volume that you originally considered. Okay? So here, in this equation here, I kind of typically put R outside the volume that I have, and the R prime here is integrated everywhere inside. And this integral here is also, this R prime is now everywhere on the surface. Okay? It happens that this formula is also valid inside the piece, but for more subtle reasons that have to do with how you average things. You remember when we solved Laplace's equation, we showed that theorem that said that the value of the potential on a kind of spherically symmetric bubble outside your point is equal to the value at the center. Actually, this statement, this fact, glorified to all this setting here, shows you that there is a completely consistent interpretation of your electrostatic potential, even inside matter, based on this idea, provided you agree that that inside the piece of matter, you have to do an average over a little region on the atomic scale, and then it works out. This discussion actually is included in the lecture notes, also in the Purcell-Morin book, in the Griffiths book, and many other things. So I think it's, again, a thing which is good to do once, but I'm not going to insist on it very much. I mean, please have a look at it. It's an interesting fact. It's an interesting thing. It's actually, so today we're kind of giving you new exercises, and then you've got an extra pair of exercises that have to do precisely with that point. But these are like side things for your enjoyment on the side. Okay, so not super practical like these things. Okay, so let me maybe just illustrate this a little bit with drawings, because I think once you've seen the drawings, you'll really understand what goes on here. So let's imagine that I have I don't know, something simple. Let's imagine that I have some kind of box in which I'm going to put a bunch of electric dipoles. And all the electric dipoles are going to be conveniently oriented in the same direction, plus minus, plus minus, plus minus, plus minus, etc. Okay, again, my fabulous drawing talents make it boundlessly clear what I'm talking about. So if I look at this chunk of matter in which I've got a completely uniform density of dipoles, this piece of matter has a polarization which is the same everywhere inside the piece of matter. Okay? Because I go here, I go here, I go here. I look microscopically. I count my dipoles per unit volume. They're all pointing the same way. I've got the same density. It's all the same. So the polarization has no spatial dependence in here. But you see, as far as the electrostatic field is concerned, I can look at little sub blocks of things. So for example, if I look at this here, there's a residual negative charge here and a residual positive charge here. And these things are like very close to each other. So there's kind of a cancellation. If I put a dipole and then I put another dipole, just imagine what I'm doing here. I'm putting dipole, 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 dipole. I'm doing a big tower of dipoles. Then what occurs when I do this tower of dipoles is that all these things in the middle cancel. And I'm only left with an equivalent thing which has zero charge in the middle, a plus charge on the upper surface, and a negative charge on the lower surface. Okay? So sigma bound charge is the polarization vector dotted into the normal unit. So here I imagine that I have my polarization, which is just going everywhere up the same way. The charge kind of cancels everywhere except at the surfaces. And I get a positive charge density here and a negative charge density there. Okay? So you've got your chunk of matter, lots of dipoles everywhere. But at the boundary, they're not compensated. So that's your surface bound charge distribution. And now, if I imagine that in my piece of matter, my polarization is not uniform. If my polarization is not uniform, then these dipoles are not compensating each other fully. Okay? So you see, if I imagine that I've got like a very strong dipoles here and then getting weaker and weaker, like this. So what does that mean? You see, if I look at what I've got here, I've got kind of an excess of negative charge because this negative is bigger than this positive in absolute terms. So if my polarization is increasing this way, I've got like an excess negative charge as I go around. And that is why the bound charge density inside is minus the divergence of P. Okay? So you can try to visualize what happens when you've got spatially varying polarization like that, and what that represents in terms of an equivalent uncompensated electrical charge. And then you'll come to this conclusion. But we've derived it like mathematically with this. Okay? And I insist on the word bound. It's a bit kind of misleading because they're not really completely pinned in place. They're mostly pinned in place. These are charges that are not mobile. They are fixed to atoms, molecules, and whatnot. They can move, but they remain essentially in the immediate vicinity of where they came from. And that's why we call them bound. Okay, so once again, molecules deforming and rubber kind of reacting to this. Charges move around, but they don't start flowing. Okay, so that's the nomenclature here. Question?